Hey, so today we're just going to do a quick problem from the SOA Exam P practice problems. This is question 147. So the amount of a claim that a car insurance company pays out follows an exponential distribution. So let's just go ahead and sort of note that. We're going to say X is distributed exponentially. And we're going to say just mean lambda, right? So if we were going to write out the PDF, not that we need to, but it'd be 1 over lambda e to the negative x over lambda, right? This is the distribution we're working with. By imposing a deductible of D, the insurance company reduces the expected claim payment by 10%. So let's define another random variable y. For another problem, this might be more explicitly helpful, but this variable y is going to be with the deductible, so we're going to pay 0 if 0 is less than or equal to x, referring to this x, because this is the without the deductible price for for x between 0 and the deductible, and then we're going to pay x minus d if we are greater than the deductible, right? So okay, and we're also told that the under y, the expected value is going to be reduced by 10% from x. So to record that, we're going to say that the e of y is equal to, if we're reduced by 10%, that means we're 90% of e of x, right? Now, for an exponential distribution, you should probably know this, so the expected value is going to be lambda itself. So we're just going to say this is equal to 0.9 lambda, right? So let's go ahead and what's the question that's being asked? Calculate the percentage reduction on the variance of the claim payment. Okay, so variance of the claim payment. That would be the variance of y. And what we're looking for is the reduction of that compared to the variance of x. So before we think about the variance of y, variance of x is just lambda squared, right, for an exponential distribution. So if the expected value is lambda, the variance is going to be lambda squared. We can also, for free, we get from this that the expected value of x squared is equal to the variance plus the squared mean, right? Just rearranging the common formula. And what we get is that this is lambda squared plus, and then the mean is lambda, so we're squaring that. So that's just 2 lambda squared, right? And this might be useful, might not be. Let's just keep going now. We're interested in finding variance of y, right? Now there are many different ways of finding variance, but one of the most common is e of y squared minus e of y squared, right? This is the common way that we do it. And we already know what e of y is, right? We already know that's 0.9 lambda. So what we really need is this guy right here, e of y squared. So let's think about it. How can we go about finding e of y squared? Because we don't really have much information, right? We don't have a ton. But what we can do is we can condition, right? We can always condition and sort of get us somewhere if there's something to condition on. And in this case, we can condition on whether or not we're below the deductible price or we're above the deductible price. So we can say that this is the same thing as the expectation of y squared, given that let's talk in terms of x right now. We'll just say x is less than or equal to the deductible. Times the probability that x is less than or equal to the deductible. It's just coming from the law of total probability, right? Plus the expected value of y squared, given that x is greater than or equal to the deductible, times the probability that x is greater than or equal to the deductible. Okay, so we're here, and this is all well and good, but at this point, we still don't really, know what's going on that much, right? But we can sort of start to see where we're going, right? If we're less than the deductible, then what is y? Y is 0, right? By our construction of y, if we're less than or equal to, sorry, that was a wrong one. If we're less than the deductible, then we're paying 0 anyway from the point of view of the insurance company. So this whole term is just going to go to 0, right? And so really this is just e of y squared, given that x is greater than or equal to the deductible, times the probability that x is greater than or equal to the deductible. And so from here, what can we do? Well, we sort of need to figure out what this guy is, the probability that x is greater than or equal to the deductible. And sort of what we can do right now is we can take a look at just this e of y term, right? Because we know what e of y is. It's equal to 0.9 lambda. So maybe we can get this guy using the same process, right? So we'll go to e of y. And we'll condition on this guy now. So we're going to say e of y given x is less than or equal to d, p that x is less than or equal to d, plus e of y given x is greater than or equal to d, p that x is greater than or equal to d, right? And this is, we're still just working, in total probability land, right? Again, if we're less than the deductible, then the expected value just goes to 0, right? So we're going to cross that guy out. We're going to say that this is just equal to e of y given that x is greater than or equal to the deductible, times the probability that x is greater than or equal to the deductible. And let's just remember real quick, we already know what this is, right? This is equal to 0.9 lambda, right? So we'll just write that in, 0.9 lambda. All right, great. So we're making progress here. We're making progress. So when we're talking about expected value of y, given that we're greater than or equal to the deductible, well, at this point in the support, if we're greater than the deductible, then what we're talking about is the expected value of x minus d, right? That's what we're talking about. We're talking about the expected value of x minus d, given that x is greater than or equal to d, times the probability that x is greater than or equal to d, right? This is where we're going to use the memoryless property, right? Anytime we have an expected value or a probability, right? Either one, in the case of an exponential or a geometric distribution, if we have x minus d given that we're greater than or equal to d, let's just sort of visualize this, right? If this is the point, let's call this the point 0, let's call this the point d, right? And we'll say that, it goes on and on forever. Well, then if x is greater than or equal to d, and we're thinking about the expected value of x minus d, well, we're going to take and pick this line up, and we're going to shift it back to 0, right? That's what we're doing. We're saying x minus d, given that x is greater than or equal to d. Well, we're just shifting all that back, and because of the way that the exponential distribution works, these expected values end up being the same as if we were to just consider the expected value of x given that x is greater than or equal to 0. Right, is the same thing as, just to be clear, is equal to the expected value of x minus d given that x is greater than or equal to d, right? And this is just your typical expected value, right? Again, to be clear, because, we're just talking about, given that we're in the support of an exponential distribution, what is the expected value of x, right? That's just e of x. Just to be clear, right? So that was all just to, hopefully help understand this memoryless property a little bit more, right? So this is then just using that, what I was just talking about. This is just the expected value of x, right? I guess I'll write given that x is greater than or equal to 0, times the probability that x is greater than or equal to the deductible, right? And again, we're still equal to 0.9 lambda, right? But this guy is just lambda, right? It is at this point. This is just lambda times the probability that x is greater than or equal to the deductible. And remember, this is what we wanted to find here. And this implies automatically that the probability that x is greater than or equal to the deductible is equal to 0.9, right? Because 0.9 here, and then lambda, you divide, right? Okay, so now we have the piece that we were sort of looking for. And we can go back up here now to this guy, right? And we can say, okay, let's just go ahead and take a look. We're still looking for e of y squared, and we've already determined that that's equal to the expected value of y squared, given that x is greater than or equal to d, times the probability that x is greater than or equal to d. And we already just found this piece. This is equal to 0.9 here. So let's go ahead and break this down a little bit further. Again, using the same logic, when we're in this portion of the support, when we're greater than the deductible in d, the expected value of y squared is just the expected value of x minus d squared, given that x is greater than or equal to d, times, and then I'll just say times 0.9, right? So, okay, this is where it's, again, helpful to know your memoryless properties. It actually, the way that this works is that we can take any function of g of x, and let's just say g of x minus d, given that x is greater than or equal to d. This is always going to be equal to the expected value of g of x, given that x is greater than or equal to 0. right? And so again, what we're just saying here is this can be any function, right? This could be, you know, the exponential function, cubed to the fourth, right? Whatever. We can just go ahead and take this minus d out if that's where we're starting in the support, right? So here we're squaring it, but that's okay. We can just say that this is the same thing as e of x squared, right? And oh, wait, we know that already, right? We figured that out already. E of x squared up here. Let's go and we found this when we were just getting it for free, right? It's 2 lambda squared, right? So let's go ahead. This is the same thing as 0.9 times 2 lambda squared, or 1.8 lambda squared. Well, great, we're almost done now. So let's go back and take a look. We have e of y is equal to 0.9 lambda. We have e of y squared is equal to 1.8 lambda squared. So we have what we're looking for is variance of y, which is equal to e of y squared minus the mean of y squared, which is equal to 1.8 lambda squared minus, and then we have what we already found this guy, or we were sort of given this guy. It's 0.9 lambda. 0.9 lambda squared. This is 0.81, right? So 1.8 minus 0.81 is going to be equal to 0.99. 0.99 lambda squared, right? And so then we can go ahead and just think about it. If the variance of x, var of x is equal to lambda squared, and the variance of y, is equal to 0.99 lambda squared, well, then we have a reduction in variance of 1%, right? A 1% reduction in variance. So then the answer would be A. And I hope this was helpful.